Hello, welcome back to Decaf-Math ASMR, and a warm welcome if you are new here. Today, let's take a look at a problem. It's an optimization problem, and we can use Lagrange multipliers, or the idea of the Lagrangian, to help us solve it. So we'll see how it goes, and if nothing else, this is actually a pretty tedious question, so maybe it will lull you to sleep, and I thought we could just take it nice and slowly, and I just invite you to relax with me. So it is raining outside right now, so you might be able to hear it. I'm not really sure, but I hope it doesn't bother you. So this isn't formal or anything at all. I haven't really totally worked this out, so hopefully it goes well. But here we go. So we can do a little bit of review too for finding partial derivatives and stuff, but so for this question, we're going to keep it like the storyline basic. We are going to try and make a box, and we have 24 squared centimeters of cardboard. It's just a random number, and it's going to be an open box, so we don't have a lid. And the question is, what is the maximum volume that we can make? So what is the maximum volume we can get for an open box slash no lid, right? So it's just a box with no lid, with 24 squared centimeters of cardboard. Something like that. Okay, so this is an example of an optimization question. So for Lagrange multiplier, Lagrange, love that word. Lagrange multiplier questions, that's usually going to be this setup. We have a function f of, it could be just x and y, but it could be z. In this case, there's going to be a third variable, but it can keep going, that we are going to try and maximize or minimize, depending on the question. And then there's going to be a constraint, and that's going to look like g of x, y, z may be equal to some kind of constant k. So that's the general idea. We are trying to maximize or minimize some kind of function given a particular constraint. So in this case, we can determine what our functions are. I am not so good at drawing stuff, but I'll try. So we have the base of our box, and so it'll have a height, something like this. Oh dear. Okay. I'm gonna try. Okay, maybe like that. And it's not gonna have a lid, so the top part is gone, right? But if you can picture it, we have a base, so something by something, and then usually you'll have, for surface area, you'll have two opposite sides plus two opposite sides plus the top and the bottom, but we're just not going to have a top, that's all. So we can just label it like x by y on the base, length and width, and then the height can be z. It's So that's how we'll just use our x, y, and z here. So in this case, the thing that we are going to try to maximize is the volume. So in this case, f of x, y, z is going to be x times y times z, so literally x, y, z, because the volume of a box is length times width times height, right? So x times y times z, and our constraint here is given by how much surface area of cardboard we have. So to get the surface area, we have our bottom. So g of x, y, z is going to be, our bottom is x times y, and then we have our two xz's for this side and this side, and then two yz's for this side and the back. That makes sense. So 2xz plus 2yz. So these are from our surface area formula. So usually there's the 2xy as well, but no top. But we'll have 2 of this, 2 of this, and 1 of that, and that has to equal 24. Or be less than or equal, but we're going to focus on the boundary part. Okay, so this is our g of x, y, and z. Okay, so for these kinds of questions, the main sort of big picture idea that we're keeping in mind is that when you have two variables, so if it's just x and y, you're talking about curves. And so if you're trying to maximize or minimize a curve given a particular constraint, the optimal point, I'm without proof right now, but the optimal situation is going to be where the two curves are tangent to each other. So another way of saying that is that the tangents are going to be parallel, but then you can also say that means that the gradients, which are perpendicular to those, are also parallel. That's another way of saying it, right? And so the gradient of f is going to be some kind of constant multiplier of the gradient of g. And that lambda is the Lagrange multiplier. And another way of writing this is that if I just move this over to the other side, I can actually, well, this is another way of saying if I define my Lagrangian as x, y, z, and lambda, I can just write f of x, y, z minus lambda g x, y, z minus whatever that constant k is, right? So that is the official Lagrangian. It's a function, and it's a function of my x, y, and z and my Lagrange multiplier. So you can do all of the partials of this with respect to x, with respect to y, with respect to z, and set it equal to 0, which if you just kind of rearrange this, you can just stick with this one, because you're just moving this whole thing over. So that one's probably easier to just keep and follow, but I just wanted to show you that's where the Lagrangian comes from. So here the gradient, remember, is going to be a vector, so we're going to have the partial with respect to x, y, and z, and same for this. And so in order for the two vectors to be equal to each other, we just set the x parts equal, the y parts equal, and the z parts equal. So we're going to take the partial of this with respect to x. So partial x, y, z with respect to x is going to be, you treat the two y and z as constants, but x is the variable that we're taking the derivative with respect to. So we're just left with yz, and that's also going to equal lambda times the what's it called? the partial derivative of this with respect to x. So we're gonna look at it piece by piece, the x and the y. So we'll still have our lambda, and then the x times y with respect to x is just going to be y, and then the plus 2 and z are going to be constants because we still have an x term there. So the derivative of x is just going to be the 1. We just pull out 2z as though it's a constant. 2yz goes away because there's no x in there. Constant goes away. So that's what we're left with. So this is the partial of the derivative of f with respect to x, and then setting it equal to lambda times the partial derivative of g of xyz with respect to x. So that's one formula, and this is where it gets tedious, but it's pretty much the same. So we're gonna do with respect to y next. So the derivative of xyz with respect to y is going to be just xz. I'm just hoping I don't make a mistake here because kind of change our answer a bit. So we still have lambda. Now we're taking with respect to y, so x times y. Now we're taking with respect to y, so x becomes our constant. This part goes away, and we have plus 2z. And then the last one is going to be with respect to z. So xy equals lambda, and this part goes away now. So 2x and 2y, like that. So we have these formulas that we're trying to solve, and we have our original constraint. So we still also want this. So we have 1, 2, 3, and 4 equations to solve. So you just gotta do this however you can. We don't actually care about what lambda is here, so we can just try to get rid of it, but you just basically solve these 4, and theoretically we should be able to because we have 4 variables and 4 equations. But let's see, so I think probably the best way to do this is just, I'm seeing yz, xz, and xy, so you might as well fill in the gap. So in this case, I'm gonna multiply by x on both sides, and this one I'll multiply by y, and this one I'll just multiply by z on both sides, so that I get xyz, and yxz multiplication is commutative, so these are all xyz, right? So that means I can set these equal to each other. So if you want, you can work out this algebra on your own, but just that's what I'm seeing now. So that just means that I'm going to try and set this part together so that I can eliminate this. And so what happens? So I'll just go ahead and distribute this. I'm hoping this works out. But I have x, so lambda xy plus lambda 2xz, and then here I have lambda xy, which is good, plus lambda 2zy, and then 2 lambda xz plus lambda 2yz. Okay, so hopefully these come together, but if I set these two together for sure, I just get that lambda xy and lambda xy is here, so that lambda 2xz equals lambda 2zy. So I basically get that 2xz equals 2zy. So since z is not going to be 0, because it's going to have no volume, so that's not allowed, you can just cancel those and the 2's go away. So I get x equals y solves 2 and 3 here. And then with that, I can probably do the same thing here. So 2yz, these two parts go away, so I can set like solving 3 and 4 together. I can get x times y equals 2xz. So then, since again x is not going to be 0, I can get y equals 2z. Okay. So x equals y and y equals 2z, and I think with all of that, that's good enough to solve this now. So basically, I'm not trying to focus too much on the algebra, since that's more of like the basic calculation part, but for this kind of question. But now that we have x equals y and y equals 2z, we should be able to solve for one of them. So let's go ahead and just plug in 2z for y and 2z for x, since x equals y and y is 2z. So anywhere we have x, we'll put a 2z, anywhere we have a y, we'll put a 2z, and anywhere we have a z, we'll keep a z. So we'll solve for z first. So 2z, plugging into the constraint, 2z times 2z plus 2 times 2z, oh my gosh, times z plus 2 times 2z times z equals 24. How's that for ASMR? 2z times 2z plus 2 times 2z times z plus 2 times 2z times z equals 24. So now 4z squared plus 4z squared plus 4z squared equals 24. And so 4 plus 4 plus 4 is 12z squared. 12z squared equals 24. So z squared equals 2. And since z is the length of a side, it's going to be positive. So then z is going to be the square root of 2. And if z is the square root of 2 and y is 2z, then, and x equals y, x and y are both going to be 2 root 2. So the dimensions are going to be 2 root 2 by 2 root 2 by root 2. So that volume is going to be root 2 times root 2 is 2 times 2 times 2 is what? 8? 8 root 2. So 8 root 2 cubic centimeters is going to be our answer. What a disaster. Okay, so I think that is right. And I also should mention that this is kind of a new setup, so I don't even know if all of this is within frame, but I got a ring light, and so I'm trying this, and I'm hoping all of this kind of shows up, but I'll figure that out later. But basically, I wanted to note that it's not always the case that you, like whatever answer you get is actually the maximum or minimum. Like when in Calc 1, also, when you have these kinds of questions and you take the derivative and you set it equal to 0, while it's usually the case, you can't necessarily just assume that it's a maximum or minimum. You actually have to show it, and it's the same here. So just because we got a number, that's not necessarily the maximum, although in this case I'm pretty sure it is. So one way to kind of convince yourself is that, first of all, you have to show that it exists in the first place. Like, how do you know that there is a maximum and it doesn't just go off to infinity unbounded? And in this case, I think it's okay because we have our constraint here. So with the surface area, that means that, you know, since the lengths of the sides can't be 0, like as one increases, the other two have to decrease to keep the constraint of 24 squared centimeters. So as one increases, the other decreases, so there has to be some maximum there. And so it exists, but then how do we know? Well, we got this value, so if you really want to be like complete about it, you would probably just pick another value and show that there's nothing greater than that, because if it is going to exist and if this is it, then anything else that you pick that satisfies this constraint should not be more than that. And I think it suffices to show that just one value would not be greater. So you can do that by just finding numbers that work here for x, y, and z that satisfy this. So you can kind of, don't pick 0 because that doesn't make sense, but you know, 1 could be pretty nice to work with. So you can just pick whatever point and then find x, y, and z that satisfy this to make 24, and then find what x times y times z is and see that that is less than 8 root 2, I hope. Anyway, that's more theoretical, but I think just for the steps in general, I hope that this helps for Lagrange multipliers. So just wrapping it up, if you have a function that you're trying to maximize or minimize and it's over a particular constraint, you can take the partial derivatives for each variable, so x and y and z, and you set them equal to a lambda, which you are including as a Lagrange multiplier, lambda times the partial of the constraint. Set those equal, and you also want to satisfy the original constraint, of course. So you have 4 variables and 4 equations, or maybe 3 and 3 if you only have 2 variables, and you just solve them together, and it doesn't really matter what the actual lambda is. And then you want to solve for one of them, and then therefore solve the other variables, and then plug in back into the thing that you're trying to maximize or minimize. And that should be it. So let me know if you have any questions, and I'll see if I can dig up some practice questions or something. It's been a really long time since I've looked at this stuff, but I remember really enjoying it. So yeah, I will see you around for more math very soon, and hopefully I can continue to improve my setup and have a more regular uploading schedule. But if you are new here, I just wanted to mention that my videos kind of switch between math and ASMR, and they're all pretty much whispered or soft-spoken like this, but sometimes I have more sleepy math-centered stuff, or I'm still experimenting with ASMR and stuff like that. So just be aware if you're joining along, whether for just math or ASMR. I'm kind of somewhere in the middle, but either way, thank you for joining me in our little math nook today, and I will see you around very soon. Bye!